Alrighty, folks, here we go. I'm sad to say that I'm not in today. So we're going to do permutations and combinations. This is the first part of the next unit and the last unit that's official that we'll definitely need before the SOL and the final exam. So what we're going to do is really just talk about different ways to count things and how many options we have. And they're called counting principles, permutations, and combinations. Okay. And the first one is called the fundamental counting principle. It just says this: if the cafeteria is serving sandwich combos for lunch, they offer 4 sandwich types: ham, turkey, roast beef, peanut butter, and jelly, and 3 sides: fries, salads, and apples. How many different choices do you have? So this is like a Subway restaurant kind of, how many different sandwiches can you make with all the toppings? And it's really simple. So you have your choices for sandwich meat. You can have ham, right? You can have turkey, you can have roast beef, and you can have PB and J. And then with each of these, you have a side, right? You could have fries, you could have a salad, delightful, or an apple. And then you can see that each of these sandwich types goes to each of those, right? Different ones 3 times. And you can go all the way through and do all of these. You could probably fast forward if you wanted to. Okay. It's a little ugly because I'm not home. But basically, you get 4 choices of ham or sandwiches and 3 choices of sides. So there are 12 choices. And if you counted up all the ends of this, they would be 12 different choices. Okay. And that's really the fundamental counting principle. States that if you have one decision can be made n ways, there's 4 ways to get a sandwich, and another decision can be made m ways, 3 ways to get a side, then the decisions can be made in m times n ways. Okay. And that's the fundamental counting principle. And what we're going to see that actually um, there. Okay. So now this one, I'm going to let you guys do all the math, but because I don't have a calculator big enough here at the house to this. But police use photographs of various facial features to help witnesses identify subjects. Okay, you can read the rest. Different hairlines, eyebrows, noses, mouths, and chins. Is the claim correct that there's a billion different faces? Well, we just run right through. Um, so there's 195. Oh, that got out of hand, didn't it? Let's get that together. Come here. So there's 195 hairlines, 99 eyebrows, 89 noses, 105 mouths, 74 chins and cheeks. Okay, what does that total up to? You tell me. You can check the notes, but that's a large answer. That's a large answer. I'm going to guess it's true. A witness can clearly remember the hairline. Okay, so we know that then there's only one hairline and the eyes and eyebrows. So there's only one eye and eyebrow choices. Now I'm limiting that to 89 noses, 105 mouths, and 74 chins and cheeks. How many faces can be produced? Okay, and you can check that out as well. Okay, you can go to Desmos, use your TI, whatever, to get that answer. Okay. Now in Virginia, so that's basically fundamental counting principle, and we're going to see how that plays out. In Virginia, a standard license plate is 3 letters followed by 4 digits. How many different license plates are possible if letters and digits can be repeated? Now you can have XXX or YYY or ZZZ or whatever. Okay, so how many letters are there in the alphabet? This is always a good question. For those of you who don't know, there are 26. So the first one, there's 26 choices. And then for the second letter, there's 26 choices. And the third letter, there's 26 choices. So I'm doing 26 times 26 times 26. And then how many different numbers are there? Well, 0 to 9 is 10 digits, and there's so 4 tens. 10 times 10 times 10 times 10. So how many combinations I get? 175,760,000. Right? There aren't that many people or cars in the state of Virginia, so we know we're in good shape. Okay. Now, what if if letters and digits cannot be repeated? Okay, so this is a slightly different task. So the first choice of letters, there's 26 choices, right? But after that, I have 25 choices because I've eliminated one of the choices, right? And then the next letter, I've eliminated two choices, so there's 24 choices. And the same thing with the numbers. You can see this is a 10 for the first one, 9 because we've eliminated a number, 8 because we've eliminated a number, and 7 because we've eliminated a number. So I get 26, and you should be putting this in your calculator, times 25 times 24 times 10 times 9 times 8 times 7. And you get a slightly different answer, 78 million. Okay. This thing just really wants to do that to me today. Sorry about that. You get 78, whoops, 624,000. Okay, so permutation. How many different ways can the letters A, B, C be arranged? Okay, and you can write them here. A, B, C, A, C, B, B, A, C, B, C, A, C, A, B, and C, B, A. Right? Those are the only choices. I take the first letter and then I use the next two and I just keep rotating them. So how can we find this total mathematically? Well, simply. There are three choices for the first letter. Then there are two choices for the second letter, right? Once I've eliminated that first choice, there's two choices for the second letter and then one choice for the third letter, giving me a total of 6 choices. Okay, so here's an example. 6 swimmers are competing in the final heat for the 2,000 meter backstroke. Must be thrilling. And how many ways can they finish the race? Assume there are no ties, right? Well, there are 6 different people who can win first place. But once that first place person is in, there's 5 choices for second, 4 choices for third, 3 choices for fourth, 2 for fifth, and 1 for sixth. And you might recognize this as 6 times 5 times 4 times 3 times 2 times 1, which I think you all know as 6 factorial, right? 6 factorial. And so 6 times 5, I believe, is there's 720 possible outcomes. Okay? 720 possible outcomes that are unique to the entire race. Okay? The entire race is a unique finish. The same person can finish first multiple times, but different people finish in different places. Okay. How many different ways can 3 of the swimmers finish first, second, and third to win gold, silver, and bronze medals? So that's simply this. There's 6 ways that someone can win first. Then there's 5 for second and 4 for third. Okay. So there's 120 ways for that to happen. Okay. Because we don't care what happens in fourth, fifth, and sixth. Okay. It doesn't matter. We only care about who finishes first, second, or third. And then we say it's 120. 6 ways to finish first, 5 ways to finish second, 4 ways to finish third. Okay. And this is called a permutation. A permutation is taking n objects r at a time. And on your calculator, and you're going to see below how to do this on your TI-83, but it's called NPR. Nice. And a permutation means we determine how many objects could win medals in the race. So permutation matters. The order matters. Okay. It matters who finishes first, who finishes second, who finishes third. Those are different and unique. Okay. It's different to win first place than it is to win second place. Okay. And this is the order or the equation. So you can look at it, it's n factorial, the number of objects, and over n minus r, where r is the number of objects we're going to take, factorial. And you can see below, like I said, how to put in the calculator. So this equation, NPR, where n is 6 and p is 3, would be, it ends up being 6 factorial over 6 minus 3 factorial, which is 6 factorial over 3 factorial. And a way to look at this, right, is you could say, well, 6 factorial is 120 and 3 factorial 6. But think about it this, it's 6 times 5 times 4 times 3 times 2 times 1 over 3 times 2 times 1. So these guys just cancel out. And I'm left with 6 times 5 times 4, which is what we did on the previous page. Okay. Because we only needed the 3, the other ones don't matter. Okay. This is how you go to your calculator. Choose the math key, go over to PRB, and then select NPR. Okay. But if you have an older calculator, you're going to need to put the N first, and then you put in NPR, and then you put in 3. Okay. And here are the keystrokes, and they're on your form. Okay. You have homework assignments for 5 different classes. And how many ways can you complete the assignment? Okay. Well, that's 5. Choose 5, right? I have 5 assignments, and I'm going to choose 5. So the 5 uh, NPR 5. Okay. 5 permutation 5. You can see I'm using this right here. 5, choose 5. And that's just going to be 5 times 4 times 3 times 2 times 1. Because remember, that's 5 factorial over 5 minus 5 factorial, which is 5 factorial over 0 factorial. And remember, 0 factorial is 1. Look at that. Definitely don't want that. And that's 120. Okay. Now, how many ways if you choose 2 assignments to complete first and last? So it doesn't matter what the middle assignments are. It's just saying I've got 5 ways to choose the first assignment, and I've got 4 ways to choose the last assignment. And it doesn't matter the order I put those things in, so I don't even care about them. Okay. So I've got 5. There we go again. I've got, oh my gosh. I love that it doesn't even know that I did this. Sorry. You're like, speed it up. I get it. Okay. So 5, choose 2. Okay. That's just 5 times 4, or 5 factorial over 5 minus 2 factorial, which is 5 factorial over 3 factorial, which is 20. Okay. There are 20 different ways to choose the first and the last. Okay. I want you to do this one. and you'll come back and see your answers. Check the notes answers. Okay. Pause, pause, pause. You did that work. Congratulations. You checked your answers. You got it right. You love combination. In the previous example, the order of which the objects were chosen mattered. It mattered who came in first. It mattered what assignment we did first. That mattered. Order mattered. Okay. You would see a movie chosen on Saturday and the other one on Sunday. What if the order didn't matter? Okay. So this is when we get a combination. Okay. And not a permutation. And think about something where order matters. Think about your lock on your locker, right? The first number has to go first, the second number has to go second, and the third number has to go third. Okay. What's interesting is that we call that a combination lock. Wait for it, wait for it. When in point in fact, that's not a combination lock at all. It's a yell it out. Yep, it's a permutation lock, right? It's a permutation because the order matters on that. Okay. Now, combination, the order doesn't matter. And here's an example of that. So combination is NCR, and that's in the same place on the calculator as the NPR, math over to PRB. Okay. Domino's has a 2-topping handmade pizza sale for $7.99. Might even be a better deal now. 9 toppings, meat toppings, 18 non-meat. How many different combinations are possible, assuming the person orders 2 different toppings? And you should notice that pepperoni and mushroom results in the exact same pizza as mushroom and pepperoni. It doesn't matter the order in which we put those on. Okay, it's still it's still it's still the same thing. Okay, order doesn't matter. It doesn't matter if I put the mushrooms on and then the pepperoni or vice versa. Okay, so that's a total of 27 pizzas, right? And what NCR does, so this would be 27, choose 2, right? 9 meat, 18, that's 27 total toppings, and I'm going to choose 2. So how many do I have to choose from? I have 27 factorial over R. How many did I choose? 2 factorial. And what that 2 factorial is, and then we do the 27 minus 2 factorial. So that ends up being 27 factorial over 2 factorial times 25 factorial. Now, the easy thing with this is to say, well, look, it's obvious. I'm going to extend the page here, folks. It's obvious that um, that it's similar to a combination. What this 2 is, so the 27 factorial becomes 27 times times 26, right? And then the 25 factorial eliminates everything after that over 2 factorial. And that 2 factorial eliminates repeats, okay, when we're choosing 2. It eliminates mushroom and pepperoni being the same as pepperoni and mushroom, okay? So you eliminate the choices that are repeated. So we do 27 times 26, and then we divide that answer by 2, and there should be 351 different ways to do it. Okay, 351 combinations. Because the order doesn't matter. And that's the key. You've got to keep thinking, does the order matter? Does the order not matter? Okay. Practice. The name of 11 students who have perfect attendance. That's not me this quarter. Are placed in a hat. A teacher will reach into the hat and select the 3 names at a time. Each of those students will win the same prize. How many different groups of 3 winners can be chosen? Okay. So the question becomes, does order matter? Since every winner gets the same prize, does order matter? Pause, pause, pause. And of course, you're yelling inside, going, no, because it doesn't matter if I get chosen first or third, I'm getting the same prize. So if order doesn't matter, I'm looking at a combination. combo. What formula needed? We need N CPR. So N choose R combination. Okay. So 11 kids into the hat. That's 11 choose 3. So we know that's 11 factorial over 3 factorial times 11 minus 3 factorial, or 11 factorial over 3 factorial times 8 factorial. Now think about that. That's just 11 times 9 times, times 10 times 9. I'm going to start that little over because that was brutal. So that's just 11 times 10 times 9, and then times 8 factorial. So I'm eliminating those, right? Because this is just times 8 factorial, and that cancels with that. And then over 3 factorial, which is 6. Okay. That's eliminating the repeats. The 3 factorial is eliminating the repeats. So 11 times 10 times 9. And I'm going to divide that by 6. And I get 165. 165. Okay. if I did it, if I did an NPR, if I did a permutation and said the order mattered, then first, second, and third would be different, and I would have 990 choices. But because 160, only 165 of them have 3 different, first, second, and third are combos. So those are different. Okay. Suppose that 3 different prizes. The first will get a TI 83 or TI 103 plus graphing calculator. I don't even know what that is. The second student will receive a box set of the most recent season of Pretty Little Liars. This might be an old worksheet. And the third student will receive a math dictionary. Whoa! Not the math dictionary. Boy, you want to come in third here. I'll tell you that right now. How many different ways can the prizes be awarded? Does order matter? Yeah, order matters, right? Because there's a difference between getting a TI 103 plus that doesn't exist, a box set of a TV series I've never watched, and a math dictionary. That's different. Okay, so yes, order matters. That's the first thing you want to decide. Does order matter? Yeah, it sure does. Okay. Are you looking for a permutation or combination? Order matters. It's my permutation lock. Permutation. Okay. So we're going to use the NPR problem. So 11 permutation 3. Now you can put that right into the calculator, but I remember this is really 11 factorial over, I keep hitting a button on this pen. And if I had more time and I wasn't making this morning at May 10th at 7:35, I would edit all this out. But alas and alack, I am unable to return, so I'm going to be able, I had to do this in a hurry. Okay, so this is 11 minus, 3. 11 minus 3. Let's erase that. It's just like real life where I actually make mistakes. 11 minus 3 factorial. So that's 11 times 10 times 9 times 8 factorial over 8 factorial. So those cancel. And then I just get 11 times 10 times 9, which I think is 990. Okay, so there's 990 different ways to win, because winning first place is different than winning third place. Okay. Okay, just a little reminder. Both permutations and combinations select n objects r at a time. N is the total of objects and r is the number we select. Which one will always have more? So in your head, You should be like, well, since it says combinations, you know the other choice is just a permutation. Okay. Permutations should always have more because the order matters. When the order doesn't matter, we can eliminate duplicates. Okay. Oh, look. You thought there was more, but this is just the homework. Get out of town. Do you want to do one of the problems together? Okay, this is a calculator problem. Let's just talk about this number 4 because people get confused about how many cards are in a deck. There are 52 cards in a deck, and each suit has 13 cards. 13 cards per suit. Okay. So that's hearts, diamonds, if you remember this, spades, and what's the last one? Hearts, diamonds, spades, and clubs. We used to call them puppy dog feet when I was a kid. Okay. Oh my gosh, you guys are going to be done with this homework in 30 seconds. Okay. Here's the deal. And I'm going to post this on Schoology because I know some people, and you know who they are, they like to read better than listen. If you're in first period, give a shout out to check in on people you know who probably aren't doing this and elbow them and ask them to do it. And you know who I mean. If you're in eighth period, 100% look over to what you know is going on. Okay, here's the deal. Um, I will be back tomorrow. Um, I was unable to come in today um, for everybody's safety, but I am going to be able to come back tomorrow. And I will those quizzes. They have been graded, and they are they'll be put into the grade book, and then you can get them back. So come by tomorrow and pick them up. On Thursday, we will take the test. If you want to come during third period tomorrow for help or questions, please do.